Now that we've looked at how to take Laplace transforms and take inverse Laplace transforms using our table that I've got over here, I want to talk about how we can use that to actually solve ordinary differential equations. So I want to start off by taking a look at a real general example. So consider the following very general example of, in this case, a second order differential equation. Let's say that I want to look at ay double prime plus by prime plus cy equals some function that we'll call f of t. And let's give the initial conditions that y of 0 is equal to some value y naught, and y prime of 0 is equal to some other value, let's call it v naught, because you can think of it as oftentimes an initial velocity if this turns out to be like a differential equation representing a mass spring system, for example. So this is the equation that we're dealing with. I want to take the Laplace transform of this equation and kind of go from there with the algebra that we're going to face. So the next step would be to take our Laplace transform of the whole thing. The Laplace transform of y double prime and y prime show up in the table. We derived them in a previous video. They're down here at the bottom of, I'm using right now table 2 of the ones that I provided. It's the more compact version. And they show up right down here at the bottom. So equation 35 down here is f prime of t. And if I just go across, equation 36 is f double prime of t. So I'll be able to take those Laplace transforms. So remember, when we take a Laplace transform, it is an integral transform. When we take the Laplace transform of the whole thing here on the left, we can break it up and instead of taking the Laplace transform of basically the sum of these three separate components, we can take the Laplace transform of the three separate components and then sum those because it is a linear transform. So basically what I'm suggesting is just keep in mind that when we do the Laplace transform of ay double prime plus by prime plus cy on the left, and get that has to be equal to the Laplace transform of our f of t, whatever that happens to look like, what we're going to get out of this is really, due to the properties of linearity, I'll be able to factor out any constants from the Laplace transform, and I'll be able to split up this Laplace transform of a sum into a sum of Laplace transforms. So I can rewrite this as a times the Laplace transform of y double prime plus b times the Laplace transform of y prime plus c times the Laplace transform of y. And that should be equal to, again, the right-hand side, the Laplace transform of our f of t. So this is how we're going to do it. We can break it up like this due to the linearity. So what is the Laplace transform of y prime? Well, down here in our table, I have the Laplace transform of f double prime. All we would need to do to deal with y double prime instead is basically replace the f's that show up here with y's. And our usual notation, if lowercase f transforms to capital F, then lowercase y will transform to capital Y. So I'm just going to basically use this and plug it in right here. So we're going to get the following, and it's going to be kind of a long expression, so let's get some room here. First, I'm going to have a, and that a is going to be multiplying the Laplace transform of y double prime, which is right down there. So it's going to be s squared. I'm going to do capital Y of s minus s times y of 0 minus y prime of 0. So again, I'm basically copying this expression right here, replacing all of the f's with y's, because this is for f double prime, but we're doing y double prime. So here's what it looks like. And this is going to always be what you do when you do y double prime. It will always transform to this expression right here. To that, I need to add b times the Laplace transform of y prime. We just said that was over here, number 35 in table 2. So it's going to be s times capital Y of s minus y of 0. And then the last term, where we're taking just the Laplace transform of y, is going to be plus c times just capital Y. And all of that's equal to the Laplace transform of f of t. The notation that we use for that is capital F of s. So if I kind of zoom out here and look at the whole thing, this is our expression. This equation up here, when we took the Laplace transform, we wound up with this equation down here. So this is our function of s. This exists in what I've been calling our quote-unquote Laplace space, so to speak. And it's an algebraic equation. These values, notice there is a derivative, the y prime, but it's y prime of 0. It's just our initial condition. These values have to be specified anyways. They're given as initial conditions, and so we can simply go in and plug these things in. So if we clean this up a little bit, what I'm going to do is I'm going to collect all the terms that involve like this capital Y of s. I'm going to factor them all out together, and I'm just going to rearrange the way that this all looks. And this is the algebraic step that we always want to do. The first step after you've got it written out is to group all the capital Y of s terms together and factor them out. So what we're going to get from this is my capital Y of s, and we're going to wind up with, I'll have as squared times that first one. So there's an as squared. For this second one, I have plus bs. And then for the last one, I have plus c. So there's that term. And we'll be left with these remaining terms. So we've taken care of basically this term, and this term. The three remaining terms we'll pull out and group them over here, basically. And if you want, you can kind of even group the two y of 0 terms together. So let's do that. I'm going to group the y of 0 terms together. So it's going to be y of 0 times, and I already factored out with a minus sign because it shows up with a minus sign in both places here. So it's going to be times as for this first one and times b for the second one. So this is going to be as plus b. And then the last term, so now I've taken care of that one. And the last term that we have right here is this one. So it's going to be minus y prime of 0 times its remaining coefficient, which is just a. And again, that's all equal to our f of s. Our goal is going to be to solve for this capital Y of s. The reason that we want to solve for capital Y of s is because in the original differential equation, we want to solve for lowercase y. Right? If this was a differential equation that was given to you, the goal of one of these differential equations is to solve for y. In the equivalent Laplace transformed version of that, capital Y of s is the equivalent of our lowercase y. So once I solve for this capital Y of s and have it by itself on one side of the equal sign here, what we'll be able to do is take the inverse Laplace transform of that result of our capital Y of s to get us back to the lowercase y, which would be the solution to the original differential equation. So that's going to be our procedure. We start with the differential equation, we take the Laplace transform, solve for capital Y. Once we have capital Y solved for it, then we take the inverse Laplace transform and have the answer to the original differential equation. So that's our next step. Let's solve for y of s. I'm going to move these guys over to the other side of the equal sign, and then we're going to divide by this expression right here. So what we get out of this when it's all said and done is that our capital Y of s is going to be equal to, what am I going to wind up with over there? I'm going to have, let's see here. I'm going to have f of s on this side. And then I'm going to add these two terms over to the other side. So we're going to have plus our y of 0 times as plus b plus y prime of 0 times our a term. And all of these are going to be divided by this big mess here. So the whole thing will be divided by as squared plus bs, sorry, not b squared, plus bs plus c. So again, all I've done is keep this term over on this side, move these two terms over that side, and then divide through by this expression that's multiplying the y of s term. This is going to be our big ugly mess that we have to figure out how to inverse transform. And in general, what you'll want to do is basically do a bunch of the same type of algebra that we've been doing to make this look like something that shows up in the table over here. And we're going to do that typically by kind of splitting it up into the separate pieces and working on all the pieces separately. So this looks like one big hideous mess. We'll split it up algebraically as much as we can, and then from there we will use partial fractions to rewrite each term in a different way that makes it look like something that appears in the table here. But one thing I do want to mention is one thing to keep in mind for when it comes to higher order differential equations. If we look at these coefficients of the y of s term, the y of 0 term, and the y prime of 0 term, what you'll notice is basically this trend is going to continue. So let me just mention this. It's not super important when we actually do problems, but it is nice if you are trying to go to higher order differential equations, which we're not really going to do in this class, but just worth noticing. So notice the trend in the coefficients of the y, capital Y and lowercase y terms. So basically, if I look at them, the capital Y of s term, its coefficient looked like as squared plus bs plus c. The y of 0 term had a coefficient of as plus b, and then the y prime of 0 term had a coefficient of just a. This trend will continue, so if we were dealing with a third order differential equation, this term would look like as cubed plus bs squared plus cs plus d, and then this one would look like, one order less than that, and then one order less than that, and then we'd have yet another initial condition on y double prime, because it would be a third order differential equation. We'd need 3 initial conditions, and it would be the one that would look like a. So just keep that in mind. This pattern generalizes for higher order ODEs. But again, in this class, we're going to stick to second order on these things. Okay. So once we have our capital Y of s solved for, we simply need to inverse transform. But unfortunately, this is where all the hard work comes in. So I say simply, but it's not actually that simple. So inverse transform it to find y of t, which is the solution to the original ODE that we were wanting. The algebra that's required, it will generally depend on the form of our characteristic equation, and I should have mentioned this as well. Notice that this exactly matches the form of what we normally use as our characteristic equation for an equation like this, right? Normally we would use m. So if we were not solving this with the method of Laplace transforms, the first thing we would do would be to try to solve the homogeneous version, and we would be trying to solve for m in the equation a m squared plus b m plus c. This takes that exact same form, but we've replaced our m's that we're normally trying to solve for with s's. So this is the form of the characteristic equation, basically. The coefficient of our y of s matches the form of the characteristic equation, and it winds up being the denominator 100% of the time, the denominator of our y of s that we're trying to solve for. So that's going to play an enormous role in basically what the algebra here looks like. How does the algebra to clean this term up proceed? The algebra required depends on the form of that characteristic equation. So basically, if it has real and distinct roots, or if it has complex roots, or if it has repeated roots, all of that will dictate the procedure that we're going to use. And then also, it will depend a lot on the initial conditions. If the initial conditions are 0, it makes our life a lot easier because it kills off this whole term and this whole term. So when I say it depends on the form of the characteristic equation, what I mean is real roots or complex or repeated, etc. And again, whether any initial conditions are 0. If they're 0, it makes our life a lot easier. The process basically will then boil down to 2 steps, but they're hard steps. So the process becomes essentially step number 1, factor or complete the square of that characteristic polynomial that's in the denominator. So factor, in the case of basically if the roots are real, or complete the square if it has complex roots of that characteristic polynomial, the characteristic equation in the denominator. And then step number 2, everybody's favorite, partial fractions. If I can write, there we go, partial fractions. So that's going to be our approach. So again, let's do a real example. We did one totally generically, but you're going to get a big ugly expression from the algebra, and the goal is to clean up that big ugly expression into a bunch of discrete separate pieces that look like things that show up in our table. So we're hoping to find lots of things that look like this, right? Our sines and cosines are common, we know. Terms that look like exponentials times sines and cosines. So down here, lines like 19 and 20, those are going to be common things we're looking for. So again, if you can, have this table basically pulled out and sitting by your side while you're working on these problems. But for us, let's jump into an example. So let's start with a semi-straightforward one and see what it looks like. So let's start with a first order differential equation just to make life a little bit easy, and then we'll work our way up to a second order. So let's solve the following. I want to solve y prime plus 2y equals the sine of 4t with the initial condition that y of 0 is equal to 1. Okay, so there's our differential equation. Obviously, we have techniques that we could use to solve this. Right, it's a linear differential equation, so we would be able to solve this using integrating factor with our techniques that we had back when we were working on first order differential equations. So we know what the solution can look like. We can always use that to double check our answer if we have any doubts. But for now, let's solve this using Laplace transforms. Okay, so that's what I'm going to do. The first step is going to be to apply our Laplace transform to the whole thing. And this will be the shorthand notation I use. You're welcome to copy this or borrow this notation if you'd like. But basically, we're going to apply the Laplace transform to the whole thing. And so what will y prime look like? Well, we just did that a minute ago. Y prime matches this form right down here, right? Here's f prime. So y prime will look like s, capital Y of s minus y of 0. So that first term, the coefficient is just a 1 sitting out in front of our y prime term. And we're going to get s times capital Y of s minus y of 0. So these might be worth committing to memory, what the Laplace transform of our first and second derivative look like, because they're going to come up so frequently. Every single problem you're going to have to do this, so it might be worth just kind of eventually memorizing those. You may memorize them accidentally by virtue of having to do them so much. So we've so far Laplace transformed just this term. The next term is going to be plus 2 times the Laplace transform of lowercase y. Well, that's just capital Y. And then on the right-hand side, what is the Laplace transform of sine of 4t? And so I have to go to my table here and say, okay, up here at the beginning, here's what sine of at looks like. So sine of 4t, all I need to do is replace the a with the number 4. And I will wind up with 4 over s squared plus 16, but I'll just keep it written as 4 squared. It's totally fine. So there's what that looks like. At this point, I'm going to try to solve for our capital Y of s. And in the same step, I'm also going to plug in our initial condition y of 0. So we're going to actually replace this with whatever value the initial condition is given as in the problem. So in this case, I'm going to factor out my y of s. You notice our characteristic equation in this case will be linear. It's just going to be s plus 2, and sure enough, those are the coefficients. We have an s here and a plus 2 here. So it's going to be y of s times s plus 2. From that, we are going to subtract off y of 0, but what is y of 0? It's simply 1, and that's equal to our 4 over s squared plus 4 squared. So there's what that looks like. And now our goal is going to, again, be to isolate the y of s. So I'm going to move this 1 over to the other side. Then I'm going to divide the whole thing by s plus 2. And we're going to find out that capital Y of s is going to be equal to, so I'm going to have 4 over s squared plus 4 squared. I'm going to have a plus 1. And then both of these are, again, getting hit with a factor of 1 over s plus 2. So basically, I'm going to move that over, and then I'm going to divide by s plus 2, all in one step here. So let's write that out. In fact, let me give myself a little more room here. So I'm also going to wind up with an s plus 2 in that denominator, and then the plus 1 will only have the s plus 2 in that part of the denominator. And our goal at this point is leave this broken up, leave these terms separate. We don't need to try to combine them into one term and then go from there. Leave them separate and just tackle them separately. This term here is going to be really easy because it's already in a form that can be inverse Laplace transformed. If we come back over to our table, it looks exactly like this form right here. Equation number 2, e to the at looks like 1 over s minus a. Well, that's what I've got, 1 over s minus a, if my a were to be negative 2, right? 1 over s minus a negative 2. So that part's going to transform easily. This part, not so much. This part looks a little bit worse than what we've got down in any of these spots over here. So this one's going to require some partial fractions to kind of clean this piece up. So let's keep this one by itself. So let's not touch this one over here, untouched. Let's just focus on this one, and I'll try to use kind of different patterns to see how we're going to kind of deal with each one of these for now. So in this case, you'll notice that we have, in this case, for this denominator down here that we're going to wind up dealing with, we have one term that's going to have imaginary roots, right? S squared plus 16. The only values of s are going to be plus or minus 4i that would make that go to 0. But over here, we have a real root. So this is going to be our next step, is to basically just clean this piece up here. So let's rewrite this term, in the following way. I guess it's basically already a completed square version, so let's break this up and jump straight to partial fractions here. So keep in mind, this term over here on the left is going to have complex roots, right? That's our initial, that is this piece. It's due to the sine of 4t that showed up on the right-hand side. But this piece is linear and has a real root. So this part has two complex conjugate roots. This is a real root. And so let's split this up and try to rewrite, let's write that down. Let's rewrite this first term. So let's rewrite this term using partial fractions. Okay, so all I'm trying to say is let's rewrite 4 over s squared plus 4 squared times the s plus 2 as, what do I need for the real root? Well, it's just going to be a over some s plus 2 term, plus for the other term, remember it's a quadratic term, so we can't simplify this piece any more than it is. It's going to look like s squared plus 4 squared, but we need then a linear term on top, and that should look like, in this case, bs plus c, but if I'm smart, I'll do c times a factor of 4. Okay, why do I want this extra factor of 4 here? We don't need it, but you'll recall, so hopefully maybe let's do this as a side note. So recall the form that we used for differential equations, for partial fractions on terms that had quadratic roots looked like this. We would do basically a times s minus whatever the real part is. So if the roots are, I think we did mu plus or minus I times nu. I think those were the terms that we used. We would write it like this, plus b times nu over our completed square version down here. So s minus mu squared plus nu squared. So here's our completed square denominator that has complex conjugate roots for the values of s. And what we want to do is match the form of the coefficient of the term. Instead of writing it just as simply as, we want to write it with the same type of shift that shows up down here. Right, so if this is an s minus mu, I want this to be an s minus mu. And similarly, instead of just doing a constant up here over this denominator, I want to match this constant times the nu, where this number over here is nu. And it makes it easier because these two forms explicitly show up in our table. So let me just point those out real quickly. What I'm talking about is, so for example, here's one of them, equation 20. Right? Instead of just having s in our numerator over the complex conjugate where we've completed the squared denominator, it's much nicer if I can match s minus a to the s minus a that shows up down here. So s minus mu, that matches these s minus a's. And this thing that I'm calling a would wind up just being a coefficient sitting out in front of the whole thing. Similarly, if we go over here to equation 19, I can't just have any constant in the numerator to match this form. I need the constant up here if I'm doing the e to the at sine of bt transform. I need the constant up here to match the number down here. So again, I need an eta up here to match the eta squared down here. This thing that looks like a squiggly v is the Greek letter eta. So over here, there is no shift being done to our s squared, right? It's not s minus anything. It's just s minus 0 if you wanted to think of it. So I just need an s up here, right? It's not going to wind up matching this form that we get down here, or I guess more accurately, the form that we're going to get right here. There is no shift a. It's going to be much more similar to simply this form up here, or better yet, the form up, oh, come on now, where is it? Oh, there it is, all the way at the top. Our cosine term, this term right here. It looks like this, right? It's just an s in those two places, an s in those two places. It's not s minus anything. But for the other term over here, this term, I want this 4 up here to match the 4 down here. I could just put some constant up here, but then we would have to factor a 4 out of that constant that we wound up getting. So I'm just making that explicit. I'm preemptively factoring a 4 out. So I'll have the appropriate numerator to match the value that shows up in the denominator. So let's see how that works. Okay, so I want to rewrite this in this form. And to do that, we need to get common denominators. So the next step would be, I would need to write this first term, a over s plus 2, and I'd have to multiply it top and bottom by the s squared plus 4 squared term. And then the other term, the bs plus, I guess I can write it as like 4c over the s squared plus 4 squared. That needs to be multiplied top and bottom by s plus 2. Make it totally clear that that's all in parentheses. Okay, so there is our common denominator that we found. It matches this denominator. If this is equivalent to this and the denominators match, then it must mean that the numerators also match. So that's what we're going to compare. So compare the numerators. To get out of this, on the left we're going to have 4, and on the right I get this, so a times s squared plus 4 squared plus bs plus 4c times s plus 2. Our goal is to solve for a, b, and c. And so we need to either break this down into 3 equations. We have the option of looking at the order s squared terms, the order s terms, and then whatever terms are constants all separately. Or we can try to find convenient values of s to plug in that simplify this. Again, whenever you have a real root, you're going to have a nice convenient value of s that will simplify things. So in this case, s equals -2 will make this a 0, and it'll kill off both b and c, and it'll allow us to solve for a. So that might be a useful first step. We could also either make up other values of s to just plug in from there, or we could also compare, as I just said, the order s squared terms, the order s terms, and the order constant terms if we wanted to. So basically solve for a, b, and c in whatever way is most comfortable for you. I'm going to start by picking some convenient values. I'm going to pick s equals -2. If I pick s equals -2, then on the left side of the equation, I'm going to have 4 because it's a constant. There's nothing I can do to change that. And it's going to kill off this whole term over here. But on this side, if s is equal to -2, I'll have -2 that's being squared, so that'll be a 4. So I have a times a -2 squared plus 4 squared, which means this is going to give me that 4 is equal to, if I simplify this, -2 squared is 4, 4 squared is 16, 4 plus 16 is 20, so I get 20a out of that, and that tells me that a has to be equal to, in this case, divide both sides by 20, we get 4 divided by 20, which simplifies to 1/5. So a is going to be equal to 1/5 in this case. The next step would be to either plug in another value that we think would be interesting. Now that we've knocked this one out, things are going to be luckily a little bit easier, so we could plug in some other values of s, or again, we could choose to compare sort of the different powers in this case if we wanted to do that instead. So if I want to compare the powers of s, so let's think if we were doing it that way. The equation would be 4 equals, so basically I'm going to actually FOIL all of this out now. We'll have as squared plus this term times this will be just, we'll write that as 16a plus, foiling this out, I will get bs squared plus 2bs plus 4cs plus, for our constant, we'll get 8c. Okay, and so we could look at an alternative would look at the order s squared terms, look at the order s to the first power terms, and then look at the order 1 terms, the constants. In this case, the constants is going to be a nice one to look at. So I've got this constant, this term is a constant. So on the left we would have 4. On the right we would have 16a plus 8c. The order s terms, on the left we don't have any. And on the right we have these two terms. So we would have 2bs plus 4cs. And then for the order s squared terms, we would have just these two terms. On the left we don't have anything again, but on the right we would have as squared plus bs squared. And you can, again, in each one of these, divide out the s squareds or divide out the s's to just be left with an equation for all of our constants. So I could jump into trying to solve this, but luckily we already have a little bit of information. I already figured out the value of a different way by plugging in that convenient value of s. So these three equations down here are redundant. They're actually more than I need. I can use this equation real quickly if we wanted to solve for what c is, and then I could use this equation real quickly to solve for what b is. So let's do those real quickly. This one tells me if as squared plus bs squared always has to be equal to 0, then what it tells me is that a and b have to be opposites. This term has to cancel out this term to give me 0. So this tells me that a has to be equal to negative b, or alternatively b equals negative a. Maybe that'd be a clearer way to write it. B has to be equal to negative a. A clearer way to write it because I've already solved for a. So what does b have to be? B would have to be equal to negative 1/5. And I can use that down here in this equation, or we could come back to using the positive 1/5 in this equation. It doesn't really matter. Either of those would be fine. They should give us the same result. So let's just do this one. Again, factor out the c and divide both sides by, or sorry, not the c, factor out the s, divide both sides by s, and we'd really just have an equation that says 2b plus 4c has to be equal to 0. So 2b plus 4c equals 0. If I divide by 2, that tells me that b plus 2c equals 0. If I already know that b is equal to negative 1/5, so we can rearrange this and solve if we would like. We could solve this for c, because c is what we need to eventually solve for. So if I want to leave c on this side, I'll subtract b over to the other side and then divide both sides by 2. So c has to be negative b over 2. But we already found b. b was equal to negative 1/5. So negative 1/5 is positive 1/5. And if I divide 1/5 by 2, I'm going to get 1/10. So there's my value of c. And we can just come down if we want. So I've solved for a, b, and c just using those three equations. If we want, we can come down and verify. Maybe this will just reassure us that we didn't make any algebra mistakes, but this step is totally unnecessary. We've already used 3 separate equations to solve for our 3 unknowns. But if we want to be extra confident, let's just come and verify that this works out. That 4 is indeed equal to 16 times a, which was 1/5, plus 8 times c, which was, what was it, 1/10? Positive 1/10? Yes, positive 1/10. And so we can take a look at this. We've got 4 is supposed to be equal to 16/5 plus 8/10. If I want to get a common denominator down here, the common denominator should be 10. So I would have 4 equals, let's just do it on this side. To get 10 in the denominator, I need to multiply this number top and bottom by 2. So 2 over 2, we'll get 32 tenths plus 8 tenths, which sure enough is 40 tenths, which is indeed 4 equals 4. So it works out. The values we found for our A and C did in fact also wind up satisfying this last equation. So it looks like we got all the numbers correctly. So what does this leave us with? So we have, after all of that, the whole point of that was to solve for our y of s in a way that it can be inverse transformed. We already solved for y of s. It's sitting right here, but it's sitting here in a way that we can't inverse transform. This piece we can, this piece we can't. This piece doesn't look like anything over here. So let's break this piece up into this particular form that we just did right here, and now we can rewrite that part of the equation. So I'm leaving this one off for now. We'll come tacking on at the end, but we're just rewriting this. All that work we just did was just for this squiggly underlined term. We found out that it looks like this, where the values of A, B, and C are 1/5, -1/5, and 1/10 respectively. So let me zoom in so I can write more clearly, but let me still try to have that on the screen up there. So the value of A, we just said A was 1/5, so I'm going to just write that out in front. I'm going to write this as 1/5 times 1 over s plus 2. So that's this term. Then I'm going to do this term, the s over s squared plus 4 term, which was multiplied by b, and b was -1/5. So I'm going to write -1/5 of s over s squared plus 4 squared. So that's taking care of the first part of this term, the b portion. And now let's take care of the c portion. So plus, the value we found for c was, I think, +1/10. Yes, +1/10. So again, I'm going to write that c out in front of everything, 1/10, because if I had a 4 up here in the numerator, that's what I need to inverse transform this. What I really need is a 4 over s squared plus 4 squared. If we hadn't done this intentionally factoring out the 4 the way that we did, if I had, instead of up here writing it as 4c, if I'd simply written it c, what we would have wound up with was, after going through all of this, we would have wound up that c was going to be equal to 4/10. And we would have wanted it to be a 4 up there, and so we would have had to factor out the 1/10 to force the 4 to be up there. So I'm sparing us that last little bit of algebra of what do we need to factor out to make this numerator match the term it needs to look like by making it explicit in the form that we're guessing when we do our partial fractions. I know I need a 4 in the numerator to match the 4 that shows up in the denominator in order to match the form of our equation number 7 here, right? The a on top has to match the a on the bottom, so I just forced that from the get-go. I forced a 4 to show up, and we got a 1/10, which is now just the coefficient sitting out in front of everything. So far I've written all of these terms. I've written this part out. I've written everything related to the squiggly. We now have to, last piece, don't forget this part that was the dashed line part. So plus a 1 over s plus 2. And just to make it totally clear where these pieces came from, these pieces all came from the squiggly, and this pieces, again, came from the dashed part. And everything here is ready to be transformed. So we could potentially, notice algebraically, these two terms look the same. We could group them and just have a coefficient of 6/5 in front of them, because I've got a whole one here plus a fifth of one here for a total of 6/5. But I'm going to intentionally leave them separate. If you look in the answers in the back of the book to compare as you're doing the homework, you'll see that usually they will combine terms like that. But I'm leaving them separate for a reason, and I'll come back to that reason in just a minute. But let's transform these. So all of these functions now show up in our table over here. So let's hit this first one. This first one, so our goal is to now apply the inverse Laplace transform to get y of t, our solution, right? So the inverse Laplace transform of capital Y is back to our lowercase y. And now I just hit each one of these. So this one is going to simply be 1/5 times the inverse Laplace transform of 1 over s plus 2. And if we come back up here, 1 over s plus 2, that matches this form. As long as a is a -2, we are inverse transforming back to this. So it's e to the -2t. So this piece became this piece. Now for this piece, we're going to have -1/5. And we have s over s squared plus 4 squared. So our s over s squared plus 4 squared is, here we go, 8. That's our cosine of AT. So s over s squared plus 4 squared. So all I need is a to be 4, and it matches this form identically. So that's just going to turn into a cosine of 4t. So this transforms back to a cosine of 4t. You'll see enough of these that you'll probably be able to do a lot of these without having to reference the table. You'll see enough exponentials, sines, and cosines, and eventually exponentials times sines and cosines that they'll become kind of second nature. This one, incidentally, is going to be, so we'll have plus 1/10, and our 4 over s squared plus 4 squared is this one, number 7, sine of AT. So this one is the sine of 4t. And then this last piece, which matched this one over here, is going to be the same thing. It just doesn't have the 1/5 in front of it. So plus another e to the -2t. So if you looked in the back of the book on a problem like this, they would combine these together and call it 6/5 e to the -2t. I'm leaving them separate for a reason. I want to think about the origin of all of these terms that showed up in our solution. And I want to compare them to back at the initial problem that we were looking at. So here was our initial differential equation, way back here. Y prime plus 2y equals the sine of 4t with y of 0 equals 1. I want to figure out which parts of this equation contributed to which parts of the solution. So in general, the form of the differential equation will always partially contribute to the solution, right? This piece here is going to give us what our denominator looks like down here. The s plus 2 that showed up in the denominator down here, that's part of our solution. So if you want to think of the homogeneous version of this equation, it leads to the s plus 2 in the denominator, right? After we Laplace transformed, here's our s plus 2 that winds up surviving, that winds up in the denominator in both of these places. But this piece down here has another component. We wind up with everywhere that this s squared plus 4 squared shows up, that came from Laplace transforming our sine of 4t, right? So this term here really came from, so if we want to trace it back further, this term here that I'm squiggly underlining, it really was this term here that we then just divided by another s plus 2. So this term is still kind of that term. And from there, we go up one more step, and that's really coming from this term. And so our squiggly term originates back in the original equation. That's from the sine of 4t. The sine of 4t, if you want to think of this as like a forcing term, it's what contributed this piece to this piece to this piece, all the way down, tracing that through to the end, to this whole portion of our solution. That's essentially where that part came from. What about this piece? Where did it come from? Well, this piece again corresponds to the piece above that I wrote with a little dashed underline. Where did that come from? So where's our 1 over s plus 2 come from? Well, here it is here. Where did this piece come from in the line above? Where did this term show up from? Well, it showed up by taking this expression and moving the -1 over to the other side to become a +1. So that's really traced back to this term here. But where did that term come from? That term was our minus y of 0. This term is our initial condition. So the initial condition wound up contributing basically this portion of our solution. And we'll look at examples going forward, but the nice thing is, if you know exactly what components of the original equation contributed to which portions of the solution, right, what would the solution be if instead I gave you the exact same differential equation, but I told you y of 0 was now equal to 0 instead? Well, all we have to do is trace through this one piece. Y of 0, if it was 0 instead, that means this term would be a 0, which means this term would be a 0, which means this term wouldn't be there, which means this term wouldn't be there. And the rest of the differential equation would. So by keeping things separated in this manner, this would be a really good follow-up question on an exam problem. What would happen? How would our final solution change if the only change we made was that y of 0 was now equal to 0? And if you can do what we just did, it's very easy to say, oh, I can tell you exactly what the solution would be. The solution would be this exact same thing, but this term gone. Right? That's the only change. And that's a really cool thing, to be able to see exactly which portions. The initial condition is what provided this portion of the solution, whereas the forcing term is what ultimately led to the remaining portion of the solution, along with the form of the differential equation itself in both cases. But that's the idea here. So we can trace back which parts of the solution came from which parts of the original equation. So let's do another one. We just did this one. This was a first order differential equation. Let's do another example. Let's do a second order differential equation. So let's try one more here. So in this example, let's do, here's a good one. So I want to, again, solve a differential equation. This one's going to be y double prime plus 2y prime plus y equals 4e to the negative t. With the initial conditions, y of 0 equals 2, and y prime of 0 equals negative 1. And I want to solve using the Laplace transforms. Okay, so that's going to be our first step. Apply that Laplace transform. So let's apply the Laplace transform to this whole problem. So that first term, the y double prime, will transform to s squared y of s minus y sy of 0 minus y prime of 0. So there's what that term will transform to. How do I know? I've done enough, but it's sitting right down here. Right, it's always going to be a polynomial in s, so the first term will be s squared, the next term will be s, the last term will just be a constant in terms of s. These signs are always negative, and we just go from the capital Y of s to y of 0 to y prime of 0 to y double prime of 0, y triple prime of 0, and so on if this were a higher ordered differential equation. But again, do enough of these, and hopefully this form is something you can commit to memory, so you don't always have to look it up. The next one is going to be plus 2y prime, so I'm going to have plus 2. The Laplace transform of y prime is s times y of s minus y of 0. So there's that term, and again, it can be found in our table right here, line 35 of the short table. But again, just using y instead of f. And then the Laplace transform of y itself. So we have plus 1 times our capital Y of s. And that's equal to, on the right-hand side, the Laplace transform of 4e to the negative t. Just go up to our exponentials, sitting right, where is it? There we go. Equation number 2, this one right here. We'll have a 4 sitting out in front of the whole thing, and the e to the negative t, so for us, a is equal to negative 1, will be a 1 over s plus 1. So there we go. So here is, there we go. Here is what our differential equation transforms to. And now the goal is to solve for, again, capital Y of s. So we'll factor out that capital Y of s. It will always wind up with a polynomial that takes the same form as the characteristic equation here. So we're going to get s squared plus 2s plus 1, which indeed are the coefficients, s squared plus 2s plus 1. And then the remaining terms are, we'll have these two the y of zeros, so I'm going to get a minus y of 0 times an s and times a 2. So in this case, we're going to have an s plus 2 out of that. I already factored the minus sign out, so in this case, did I get that right? Yes, we've got that part. So here's our minus s, and here's our minus 2. I factored the minus out already. And then the last piece is this piece here. So minus y prime of 0 equals, again, the right-hand side, 4 times 1 over s plus 1. We'll now plug in our y of 0 and y prime of 0 from the initial conditions. It'd be really convenient if one of these was 0. But they're not. And we'll wind up with y of s times our s squared plus 2s plus 1. I'm going to move everything over to the other side of the equation in this step as well, in addition to plugging in those values. So we'll have our 4 times 1 over s plus 1. Moving this term over to the other side, I have to add y0. y0 is 2, so add y of 0 times this. So plus 2 times s plus 2. So this became a 2, we moved it over to the other side, and it became positive. Same thing here, add this over to the other side. We'll just have plus that constant. What is that constant? It is a negative 1. So let's just write it as minus 1. Okay, so there's what we've got. The last step is to divide by our quadratic over here. So I'll have, in one case, however we want to write this, we can write the 4 out in front if we want, whatever we want to do. 1 over s plus 1 times s squared plus 2s plus 1. So there's this piece after I've divided by this term. Now we've got this piece divided by this term. So the next one will be plus 2s plus 2 over s squared plus 2s plus 1. And then the last one is minus 1 over s squared plus 2s plus 1. Okay. And again, we can kind of choose how we want to deal with this. We could combine this all into one single term, algebraically speaking, write it all as one term, and then just try to do partial fractions on that one big term. But by doing that, by kind of recombining all of these terms, blending them together, we're going to lose the ability to do what we did in that last problem where we can trace back each part of the equation to what came before it. So you're welcome to do that, but just know there may be a problem on the exam where you will be kind of shooting yourself in the foot if you do that. I would, in general, recommend keeping them all separated out. So basically, we've kind of got 3 terms here. We'll do whatever. Call this one squiggly, call this one our dashed one, and maybe call this one triple underline or something. And we could call them 1, 2, and 3, however you want to do it. So I'm going to start with the squiggly one. So let's rewrite these. So rewrite these for our inverse transform. Okay, so let's just start with the squiggly one. So our squiggly one looks like 4 times 1 over s plus 1 times s squared plus 2s plus 1. So our first step is going to be to factor this quadratic right here, if that is at all possible. And what we'll get in this case is we'll see that this is going to be 4 times 1 over our s plus 1 times s plus 1 squared. Right, so this factors to s plus 1 squared, and we wind up getting an s plus 1 cubed out of all of this. So it's 4 times 1 over s plus 1 cubed. Okay, so there's what that denominator looks like for that particular piece. The good news is we don't necessarily have to do partial fractions on this one because it doesn't really take the form of any of the terms we were expecting down here. What it's essentially telling us is if we come back up to the original differential equation, what it's suggesting is basically the result I would get for the homogeneous solution here, because it takes this same form, is that I would get this particular form, s plus 1 squared, is what our characteristic equation would look like, which means s would be -1. And if I was looking at y homogeneous, it means the solution to y homogeneous is things that look like e to the negative t. So I'd have an e to the negative t, but it's repeated, so I'd also have a t e to the negative t. And because our forcing term matches that same form, this one's going to wind up needing to look like a t squared e to the negative t. That would need to be our guess if we were doing our traditional methods to try to solve for this. So with all of that in mind, I'm expecting that this thing should give us something where we're picking up extra factors of t because of the form of basically the way that all of these terms showed up. So let's check this out over here in our table. We're looking for basically s plus a or an s minus a raised to some power. And again, I'm expecting it to be related to some increased factors of t. And sure enough, you can see, sorry if I have some stuff on my screen here. That one's kind of a good one. This one's better. Here we go. Equation number 3, right? We've got something that looks vaguely like what we're looking for, but it just has s raised to that power. But if we come down here, 23 is even closer because it's a shifted version, right? The shifted version of s down here, the fact that it's s minus a instead, gives us a t times an exponential. So t to some power times an exponential. And that's what we're basically expecting out of this anyways. So let's just write this thing in this particular form. So I need to rewrite what we've got right here in this form. We've got s, in our case, s plus 1, so that means our a is -1. So we're going to get e to the negative t out of it when it's all said and done. And the power that we're raising to is the third power, which means in this form that n needs to be a 2, right? N plus 1 is the power sitting there. So n is equal to 2. It's going to give us a t squared over here, but that means the numerator needs to be 2 factorial. 2 factorial is indeed just the number 2, right? 2 times 1. So I need to rewrite this as 2 times 2 over s minus a -1 to the 2 plus 1. And this now gives us here's our n factorial, there's n, here's our a. That makes it match this form down here exactly. So if we apply the inverse Laplace transform to this piece, so if we were to apply the inverse Laplace transform to this one piece, we can save it for the end if we want. But what we would get out of it is that 2 would survive in front, and this, again, is going to transform to t to the second power, because that's what n is, so t squared times e to the at, and our value of a is -1. So that's what that's going to transform to. So we've taken care of this term. So let's look at the dashed term now. So this term is going to look like, what do we have? We have 2 times s plus 2 over s squared plus 2s plus 1. Luckily, we already did that factoring, so we've already done it once. Could have jumped straight to it if we wanted to. So I've really got 2 times s plus 2 over s plus 1 squared down here. So there's our s plus 1 squared in the denominator of this. So what I hope we'll notice is that if we come back to our table, there's not really anything that matches this form. The closest I find is basically the one that we were just looking at, where we're going to have some higher power of a shifted s, so like s, in this case, s minus a, raises some power. But notice the numerator needs to be a constant in order to apply this approach. Whereas up here, we have a linear function of s up in the numerator. And so this tells me that we're going to have to apply partial fractions. So what I want to do is force this to look like the following. Whenever we have a repeated root, the form that we do to get our partial fractions to work is the following. We do a over that same root to the first power plus b over that same root to the second power plus c over that same root to the third power if necessary. But in this case, the second power is the highest we need to go. So we want to basically we can rewrite this in this form. And we can choose whether or not we want to include this 2 along for the ride. We could just do partial fractions on this part and just remember to bring the 2 back at the end. Or we could keep the 2 there for the whole ride. It's kind of up to us. The last thing to keep in mind is, again, we really just want to wind up with constants here. I know in this case, it doesn't really matter what the constant is because it's going to match. So this term a over s plus 1 is going to match the form of just our exponential term up here. So that's fine. We'll just factor whatever a is out in front, and the numerator is supposed to be a 1. But this other term needs to match the one that we were just looking at, which is right here. We're going to need an n factorial in the numerator, so let's just figure out what our n is going to be. If this power right here matches this power right here, then n has to be 1 because this power is n plus 1. So 1 plus 1 would give us the second power that we're looking at, meaning I would need the numerator to also be a 1 here. So we're good. We don't need to try to factor out and force a 2 out of this or anything like that. We'll just leave it as a b because we ultimately want the numerator of this to be a 1. So just b times 1. It'll be easy to factor this out, so we don't need to do anything tricky. So let's make these two things look the same. We're going to do that again simply by getting a common denominator here. So basically, we can rewrite this whole thing down here. I'll just get it to match. And let's just include the 2 along for the ride. So let's just assume that this can be thought of as basically like a 2s plus 4 over here if we want. So maybe that would be easier. Whatever. 2 times s plus 2 over our s plus 1 squared has to be equal to, so let me make this an implication arrow. So I'm rewriting this one. What is this going to look like when we get this denominator? Well, this denominator is already there. This one I just need to multiply top and bottom by an s plus 1. So we have a over s plus 1 times s plus 1 over s plus 1. Let's toss parentheses around that, plus b over s plus 1 squared. So there's what we've got. All of these denominators are now going to match, so we can just compare numerators. And we wind up with, in this case, comparing numerators, we have 2 times our s plus 2 is supposed to be equal to a times s plus 1 plus b. So compare numerators. Just to remind us of what we're doing here. We've got two values, or 2 coefficients to solve for here. And we can pick one very convenient value of s in this case in order to do that if we want, or we could, again, just compare the orders of the terms. It's totally up to us. So in general, whenever you have a bunch of real distinct roots, the easiest thing is to always just plug in those convenient values of s. Basically plug in the roots, and you'll get a lot of simplification on the right-hand side. It'll kill off a lot of coefficients. But in the case where you've got repeated roots, right, we only have one convenient value of s to plug in, s equals -1, but it happened to be a repeated root, so we don't necessarily have a second value right off the top of our heads that's going to make life easier. On the other hand, we could compare the values of basically all the things that are proportional to s, all the things that are proportional to s to the 0th power, so constants. If there were a third term here, like an s squared term, we would do the same thing we did on the last problem, looking at the order s squared, order s, order 1 terms, basically. So we can pick and choose or combine those two approaches. It's just, in general, plugging in specific values works best when you have real distinct roots in your denominator here. And if you get to the place where you're dealing with like complex roots, you're basically going to have to go to looking at the various orders of s to make life as easy as possible. Okay, so with all of that in mind, whatever, we can either just pick and choose some values of s to plug in. Obviously, s equals -1 would be nice. So if s is equal to -1, what are we going to get out of this? On the left, we're going to get 2 times a -1 plus 2. So the -1 plus 2 will just be a 1. We'll multiply that by 2. So I'm plugging in s equals -1, and this whole thing will simplify to 2. On the right-hand side, I plug in the -1, and we get basically 0a plus b. And this immediately tells us b equals 2. So that's nice. Now that we have that, we could either, again, compare the powers of s if we wanted to. What we'll find is, so I could look at the order s terms, or we could plug in a different value of s that's not even a special one, but why not 0? Well, if I plug in 0 on the left, what will we get? We'll get 4. And on the right, by plugging in s equals 0, I will get a times 1 plus b, but we already found that b is equal to 2, so we could get this equation as 4 equals a plus 2. So what does a have to be? A has to also be equal to 2. And again, if we had preferred, we could have looked at the order s squared, or sorry, the order s terms and the order 1 terms. So this would be an alternate method, not required. We don't need to do this. We've already got a and b, but let's just verify what it would look like if we'd done it this way instead. So I'd look at the order s terms, and what I would see is that on the left we get 2s, and on the right the only proportional to s terms are as, and that would tell us that a is equal to 2. And then we would look at the order 1 terms. On the left, what are the order 1 terms? Well, we'd get 4. And on the right, what are our order 1 terms? We'd get a times 1. So a times 1 plus b. And then we would solve and say, oh, well, we already found that a is equal to 2, so we'd have 4 equals 2 plus b, and solve to find that b needs to be equal to 2. And we get the exact same result that we just got up here. So you can pick and choose. Again, I recommend the first method whenever you have real distinct roots in the denominator, and I recommend the second method whenever you have complex roots, when you're having to like complete the square of the denominator, or any combination thereof. I personally find this to be easier, so I use it as much as possible, but sometimes you're going to have to resort to this approach. So just keep that in mind. So long story short, we found that this whole mess simplifies to 2 over s plus 1 plus 2 over 1 over s plus 1. So we get, when it's all said and done, we have 2 over s plus 1. So 2 times, we'll write it 1 over s plus 1, plus 2 times 1 over s plus 1 squared. There's my a and my b. If we come back and compare them here, I basically just wrote them out in front and kept the numerators as 1s, because we need numerators to be 1s to get it to match, where's the form? Here it is, 23, to match this form in both cases. So in this case, the first term, this is our exponential. So if we were to apply the inverse Laplace transform, we'd get, what is the formatting of, I guess I wrote it all in line up there, so I'll do it the same thing here. So apply the inverse Laplace transform. That first term is going to be 2e to the negative t, right? That comes from equation number 2 up here, right? I'm writing this as basically s minus -1. So it takes this form. And this one was the form of equation 23 that we just were looking at. So this form right here with n equals 1. So that one will get 2 times t to the first power e to the negative t. So that part gives us this contribution towards our solution. So we've taken care of the squiggly part, we've taken care of the dashed part, and the last piece is taking care of just this term right here. So we just need the triple underlined term, which looked like 1 over s squared plus 2s plus 1. I think it was a plus 1 or a minus 1. Yeah, it's got a minus sign, so we can just remember to tack on that minus sign at the end, or let's just tack it on right there. Okay, so we already know that this looks like negative 1 over, we already factored that, this was just s plus 1 squared. And we lucked out. This matches the form of exactly what we just had right here, so I don't need to do any work. It's already in the form that we needed from equation 23 here, or transform pair 23, this line. So we don't need any work. We can apply our inverse Laplace transform to get, this one's going to be negative, and again, it was just 1 over s plus 2 squared. 1 over s plus 2 squared gave us the t e to the negative t. So t e to the negative t. So if we combine all three parts, we've now got all three parts figured out. We did the squiggly part, it contributed this term, the dashed line contributed these two terms, and then the triple underlined part right here contributed this term. We can combine them all together to get that our y of t, y of t is equal to the sum of all these terms that we just found. So let me go see what they all were. I know that first one was t squared e to the negative t, but what was the coefficient? 2. So 2t squared e to the negative t. That was our squiggly part. Plus the dashed part right here. So plus 2e to the negative t plus 2te to the negative t. That was our dashed line part, plus negative te to the negative t, and that was our triple underline part. So here's our solution. So keep in mind, if we were comparing this to the answer in the back of the book, they would probably combine these two terms. They both take the form of te to the negative t. We have 2 of them here, negative 1 of them here. And the answer in the back of the book would probably look like 2t squared e to the negative t plus 1 te to the negative t, which you get by combining those two, plus 2e to the negative t. But leaving it this way, again, we can trace back and say, okay, well, what happens if we, okay, going from here, the triple underline term, that came from this term, which came from this term, which was this term, the y prime term, which came from this term. And the dashed term came from this term, which came from this term, which came from basically two places, right here and right here, which really came from, those two terms, which came from that initial condition. And then the squiggly underlined piece, that squiggly piece came from this piece, came from this piece, came from this piece. So our forcing term contributed the result of this, and the two different initial conditions resulted in those two separate pieces. So coming back down here, here's what the forcing term led to, here was what the initial position led to, and here's what the initial velocity led to in terms of the contributions in the original problem. And if I said, okay, how does the answer change if I remove forcing from this problem? If we remove forcing, this term is gone, the answer looks like the remaining pieces. What happens if I remove this initial condition? I say the initial velocity is 0 now. Well, that just removes the triple underline term, which removes this one piece. So basically, by doing it this way, we can trace back, again, which part of the answer comes from which part of the original framing of the question. So I'd recommend, again, very strongly for you to try to keep your problems done in this way, as opposed to the method you'll often see is basically trying to combine all of these terms into one really big, ugly term and then applying partial fractions to that one big ugly term. I think it's easier to just keep them broken into separate pieces so we can keep track of what the exact contributions of each component of the problem were. So in the next video, we're going to do this exact same thing. The only wrinkle that I'm going to add in is a couple new forms of forcing terms that we haven't been able to deal with yet, some discontinuous functions for the forcing terms. So I'll introduce those next time, and then we will do, again, more examples just like this with those new forcing terms. They're going to show up as these pieces over here, what's called the Heaviside function and our Dirac delta function, and then something called an indicator function that's kind of a combination of multiple Heaviside functions. So we'll see that in the next video, but otherwise it's going to look very similar to what we were just doing here.